Pontzen will talk about genetically modified galaxies.
Okay, thank you very much. And thank you to the organizers for running this wonderful meeting. I've really enjoyed this week. In the spirit of a workshop, I'm actually going to show you a lot of new results today. Pretty much everything I show you is new. Most of it probably won't hit the archive for another month or two yet. So this really is stuff that I value your input on. It's about a new technique that we've been developing for maybe 18 months now, and finally is yielding its first results that are quite relevant to a lot of the things that we've been discussing. But the technique extends way beyond that, and if you want to get involved at all, please do come and chat to me before you head off. So just to say that this is work that I've been doing with a postdoc at UCL. I'm from UCL as well, which of course is the University of California in London, where the sun always shines, as you can see from this photograph here. Also with Hiranya Piris, who's also at UCL. Some of the applications to large-scale structure, which if I have time, I'll show you, although I'm going to mainly focus on galaxy formation, I've been developing with Andrzej Slozar over at BNL. But the simulations are run with Changa, and for that I've been collaborating with Fabio Governato and Michael Tremmel. Michael will fill you in a bit about some of the new physics that's being put into Changa at the moment and the exciting directions that's going in. I'm going to totally direct your attention away from the details of how the simulations run and just talk about this new technique. So let me start by taking a step back and asking why we feel like a new technique is required at all, just by thinking about some of the pros and cons of the types of simulations that we all run from day to day. So let's think about three categories: cosmology, statistics, and resolution. And let's think about different types of simulations that we run. You've all seen very impressive work done recently on pushing the boundary in terms of what we can do in terms of large volumes. We're now in a situation where, of course, we can get the cosmology. I am going to boil everyone's work down to emoji, by the way. It's the end of a long week. That's as good as I can do. So for the volumes, the cosmology is great. We pretty much know what we're doing with the cosmology these days. The statistics are becoming great. People can run really nice large volumes. But, of course, you suffer on the resolution. It's inevitable. You're never going to be able to get the kind of resolution that you would like to get when you're also simulating something that's representative of the whole universe. So you could turn the whole thing around and run some idealized simulations. The resolution in those, of course, you're going to be at the cutting edge, almost by definition. You're putting everything into one or a handful of objects. The problem is that the statistics are pretty hard to get right unless you do something really quite careful about trying to reconstruct merger histories and so on. The cosmology's just got to be wrong. You can't sit it in a cosmological environment. Otherwise, it's no longer an idealized simulation. So there's a sort of intermediate step, which a lot of us work quite a lot on, which is to run a Zoom simulation, where it kind of combines pros and cons of the two other techniques. You get the cosmology right, it's sitting in a cosmological environment, but you're putting high resolution in some small volume, and so you're doing well on the resolution as well. Of course, the problem with running these Zoom simulations is typically it's pretty hard to do anything in terms of statistics. I mean, you can run a handful of the things and try and be as representative as possible, but even if you've got 10, 20 objects, you're simply not going to cover the diversity of galaxies that we know exist in the real universe. And when you start thinking about these problems, you realize there's actually another column here that I haven't put on yet, and that's control. There's a sense in which, when you're running an idealized simulation, you have this really nice level of control that you can actually decide. You can pose a truly scientific question. You can say, okay, I have some hypothesis about the way that galaxy formation operates, and within the limited accuracy of what simulations can tell you, you can do something quite specialized. You can set up some special situation to find out whether your hypothesis is right. That's not really something you can do in a volume. You can maybe correlate lots of different properties, but that's really not the same thing. And to a certain extent, okay, maybe you can do this in a Zoom by picking special areas, but you really are never going to have the same level of control as you have with the idealized case. In particular, even if you pick a load of areas to try and get a range of some particular property, maybe, say, the time of the last major merger, the real problem you're going to have is all sorts of other things are going to be varying between all of your different Zoom runs as well. So it's going to be pretty hard to pick out what's going on with real precision accuracy. So, genetically modified galaxies are a proposition to try and fill in the gap here somehow. I was looking for a good image to represent these new galaxies, and I did a search. I was delighted to find this picture of Piero here. I think it sums it up quite nicely. The idea of genetically modified galaxies is that you do a normal zoom run, but then you go back and you revise some aspect of the initial conditions that you started from. I'm going to show you exactly how you do that and how that works mathematically. But just take it at face value for a second that you can do that. So you run a zoom run, then you go, oh, okay, I like this galaxy, but what if its last major merger were at a different redshift or were a different ratio or whatever? Then it's a zoom simulation, so it's got the cosmology, it's got the resolution. You've got control now, because you can go back and you can change your control variables. And what's kind of interesting about what I'll show you is that you also get some handle on the statistics. It's never going to be as good as actually running a volume to get the statistics, but you do actually get some information about the relative abundance of different objects that you end up running with this technique, as I'll show you as we go along. Okay, so that's the motivation behind why we would even want to do this. So here's how it works in practice. So you take a regular cosmological simulation. In this case, I'm showing you a zoom simulation. I'm just showing you the zoom region here at redshift 2. We're focusing on redshift 2 to get some interesting results, which I'll show you in a minute. But just take a look at the dark matter projected density. We can run a halo finder on this. We can identify a target halo that we want to change some aspect of this target halo. And then you can go backwards in time. So we can take a step back. We can say, in this case, I've looked at the merger tree. I know there was a merger at about redshift 3. That was its most significant merger. So I can go back to just above redshift 3, and I can identify the substructure that's falling in. So this is the thing that's going to merge in at redshift 3. It's about a 1 to 5 merger. Okay? Then I can keep going backwards in time and trace all these particles backwards all the way into the initial conditions. And this is what they look like in just a slice through the simulation at that time. And this is the point at which we actually apply some kind of modification. So we go all the way back into the initial conditions, and then we change them in some targeted way. Now, in this case, what I want to do is increase the merger ratio. So I want to see what happens to that halo if it had a more major merger at around the same time. And the way that you can do this, if you know your Press-Schechter theory, is just to take the region which it represents a substructure and increase its mean density throughout that region. That's going to make it collapse sooner and grow to the point where it's larger when it's merging into the halo at redshift 2. That's right, yeah. So that's right, yes. Well, so this is the halo at redshift 2. This is a bit of substructure that merges in at redshift 3. So by redshift 2, it's all part of the same halo. Yeah, right. But this whole thing is going to collapse into a single halo. No, it is a merging halo. So this bit collapses first in the center. This bit collapses separately. And this bit merge at redshift 3. Right. Yep. Okay. So that's what I'm going to do. I'm going to increase the mean density in here. Of course, if I do that, because of the correlations that are there, it's going to make the whole thing more massive by the time we get to redshift 2, and that's not what I want. I've decided in this case, I mean, it could be what I want, but in this case, what I want is to increase the merger ratio, but end up with the same mass of galaxy at the end. So what I do is I fix the mean density of this region, okay? So this region is going to be increased, this region is going to be fixed, and that means overall in this region will have to be some kind of compensation to make up for that. Now, of course, if you just went and changed the density manually of these regions, you would end up with something that you would never get in a lambda CDM universe. So you can't do that. But luckily, the problem of trying to set linear random fields subject to some kind of constraints is actually a solved one people know how to do this, and it's been used for a while in our field to run things like constrained local universe simulations, where you try to get something that's like our own Milky Way, for instance. And the equation looks something like this. This is a slightly different form that we find more practical to work with of an equation that appears in this paper, Hoffman and Rybak, 1991. And just without going into any detail, let me just tell you what these terms actually mean. It means that we're going to update the initial conditions by starting from the original initial conditions. This whole update operation involves the power spectrum, so you have to take that into account so that you stay consistent with being in a lambda CDM cosmology. We have to work out what these particular vectors are here, and they correspond to exactly what kind of modification you want to make. In the case I'm showing you, it's to do with modifications to the density, but you can make these vectors to make modifications to velocity, to angular momentum, and so on. And then this term at the end is basically just saying how much do you want to change the property by. And one of the remarkable things about the way this all works out is that the units of this thing, in the particular way that I've written it, are actually units of chi-squared. So it means if I make a change by the number 2 to whatever these properties are, you end up with something that's 3 times rarer. And that's what I meant when I say you get some handle on the statistics of this. Once I've modified the thing, I get some new galaxy, which in the case where I've made a modification with a value of 2, turns out to be 3 times rarer in the universe at large compared to the kind of structure that we started out with. So that's the maths. Now I'll show you what it actually does. After about 1.5 years of code development, we can go from this initial conditions to that initial conditions. It's pretty exciting, huh? Can you spot the difference? Okay, so that's the change. If you actually take the difference and plot these, just the difference field, you can see what's happening. The density is being increased here, and like I said, you've got some compensation here. But note the changes aren't completely limited to the region of the collapsed halo from redshift 2. They do spread out beyond that region, and that's because of the power spectrum. You have to do that to keep it consistent with the power spectrum. But having done that, we have a new set of initial conditions consistent with lambda CDM that we can now rerun and see what happens. So here we are at redshift 3.5 again. There's the major progenitor. Here is a bit of merging substructure that's about to merge in. This is the unmodified simulation, where, as I told you earlier on, we have this 1-to-5 merger about to happen. And when I perform the modifications and rerun the simulation with the new field, it looks like that. So you can see, hopefully, there's a bit of a change. It's not huge. Most of the large-scale structure is still in place. I'll show you that in more detail in a moment. But in particular, this substructure has got larger. This one has actually got slightly smaller, incidentally, so that the overall merger ratio is now more like 2-to-3 rather than 1-to-5. So we've turned a fairly minor merger into really quite a major merger. And if you zoom out and take a look at what the universe at large looks like, the changes are really quite tiny. So there's real meaning to saying this is the same galaxy as far as possible. It's just that we've made some particular change to some particular property of its merger history. Other than that, it's basically the same galaxy. And that means you can start looking differentially at what's changing in this galaxy as we change these aspects of, in our case, the merger history. So let's have a look at the accretion history. This is just the virial mass over time. That's the original accretion history from the organic halo. Then we knew that there was a merger around redshift 3. It barely shows up here. I mean, it all looks pretty smooth because it was just a 1-to-5 merger. And we're trying to fix the target mass at redshift 2 right here. And if you have a look at what happens in the genetically modified case, so the stuff collapses a bit faster at the beginning. Okay, fine. And then it falls a little bit behind. Then around the time of this redshift 3 merger, of course, it jumps up because you've already seen that the infalling substructure is now almost 1-to-1 merger. So you get really rapid accretion at this point, and then the things kind of join up by redshift 2 and have a pretty similar history after that. So that's what the accretion history looks like. And Nina Roth, who is postdoc at UCL that I've been working on these ideas with, has done a really nice study of the way that you can recover. It's a known relationship between the collapse scale factor of a dark matter halo and its NFW concentration parameter. And she's got a really nice discussion of how you can recover that with using just a few of these Zoom simulations, genetically modified. I don't really have time to talk about that today, but I encourage you to go and read that paper. So here's our accretion history of the target galaxy that we're talking about today. Let's take a look at the star formation history. It's a full baryonic run. It has star formation, it has black holes, and Michael will talk more about all of these details in a moment. But just take it at face value at the moment. Here's our star formation history. And if you look at the genetically modified run, it pretty much tracks the original run right up to the point of the merger, and then it quenches. So we now have a matched pair of galaxies which are almost identical, and they sit in exactly the same large-scale structure, but one of them quenches because of a major merger, and the other one doesn't. So we can begin to study what that quenching process looks like. So I can now flash between images. Here's the unmodified galaxy. There's the genetically modified galaxy. These are same virial mass at redshift 2, and if I flick between them, you might just about be able to see the difference. This thing looks like a nice, compact, quenched galaxy. And I was really, one of the highlights for me have been Reinhard Genzel's talk, this incredibly impressive work with KMOS 3D. But I'm just going to steal the idea of this plot and show you what the galaxies look like on that plot. So here are some fake images from our simulations. Here's the unmodified galaxy, pretty much tracks the main sequence and then just sits there. The genetically modified one, the major one, you can actually see there's an image of the merger taking place right there, and then it just drops straight off the main sequence. The last point is actually down here underneath the axes. So this thing really does quench, and you can actually see it go through all the phases that people have been talking about throughout this week. Okay, we can tie this to the accretion of the black hole in the two simulations, but I don't want to go into too much detail about the way the black holes work in these simulations because that is coming up in Michael's talk. So let me just finish by making a comment about why this is really useful. I mean, these results that I'm showing you, we've literally got them in the last few weeks, so we haven't had a lot of opportunity to analyze them in detail. Of course, we're going to do that and do a much more comprehensive analysis of what's going on than I've been able to show you. But there's something else that we're doing right now, which I think is even more exciting, really, to my mind, is the power of this technique. But I was showing you this mass accretion history earlier on. The point is you're not limited to having two of these things. So we're running a simulation right now. So far, we've only run a dark matter-only version. We're running a simulation right now which splits the difference. So you can simply go back to the genetic modification algorithm and say, okay, I want a change that's half as big as the change that I made first time round. And in the dark matter-only simulations, it just kind of interpolates between the two states of the original and the chi-squared=4 simulation, which is the one that I've been focusing on so far. And as to what happens in terms of does it quench, does it not quench, I think that's going to be a very interesting piece of science that we can do right there, but right now we don't have the simulations run to redshift 2, so I can't tell you any more about that. Okay, so here are my conclusions. Do I have any more time? I have 6 minutes. Wow, okay, so I can tell you something about large-scale structure and then go back to the conclusions. So I wasn't sure whether to include this, but since there's time, might be some people here who are interested in large-scale structure. So there's a kind of extreme version of this algorithm, which I've been exploring a bit with Andrzej Slozar. And it gives you some really interesting insights into large-scale structure. So I'm just going to show you those now. So here's just this is not a zoom-in simulation. This doesn't have any baryons anymore. It's just a 200 megaparsec dark matter-only simulation. Here it is at redshift 0. I can go through and run a halo finder on that simulation and take a look at where the halos are. And the color scheme of this plot is now that the intensity is showing you the density fluctuations in terms of the number of sigma in the width of the statistical distribution of densities. So white is a void and dark is a halo. And then I've used the halo finder and just colored the fraction of particles according to whether they're sitting in halos or not. It's pretty straightforward. So the halos appear blue at the moment. Now I can do what I was doing earlier on and just trace all of these particles all the way back into the initial conditions. And you can watch that happen right now. And there are the initial conditions there. I kind of like this. It looks like a kind of Petri dish or something. But the trick now is to do a really extreme version of this genetic modification. Going to leave the power spectrum absolutely the same, but we're going to totally change this density field. In fact, all I'm going to do is I'm going to flip the density field. So where I have something that's 2 sigma above the mean, I'm now going to have something that's 2 sigma below the mean, and vice versa. And of course, in the initial conditions where everything's purely Gaussian, that's an exact symmetry. So this leaves everything statistical about the simulation invariant, but it completely flips around your perspective on what's what. So now the light areas here are colored blue, and the dark areas are colored orange. And if I run this thing forwards in time, then you can see what happens. The orange areas are collapsing into filaments and halos. The blue areas have turned into voids. And remember, the blue areas were the things that were the halos in the original simulation. So by running a halo finder on one simulation, you actually identify the voids in another simulation. And it's really quite remarkable how nicely this correspondence goes. And there's a lot of interesting stuff you can do there because the nonlinear structure formation, the idea of merging voids and so on, comes out quite naturally from just sort of flipping Prashekta theory with a few minor differences. And so you can start to understand the evolution of voids in one universe in terms of the evolution of halos in another universe. And as a final comment on this, sorry? No, I'm going into the nonlinear regime. Sorry? Yeah, it's true. Okay, so there are details that differ between the way that voids interact and halos interact. And exactly this comparison can shed light on exactly those differences, right? So it tells you about the nonlinear regime for sure. You just have to be a bit careful about exactly how you construct the comparison. But I think it's pretty clear that at zero order, it does just pick out the voids, right? So where was I going with that? Yeah. So one of the nice things about this, which I totally didn't think I'd have time to tell you about this, so I didn't actually put in the slide. But it turns out that if you take the power spectrum, the nonlinear power spectrum from this redshift naught simulation, and the nonlinear power spectrum from the original redshift naught simulation, and average them, it turns out if you write out the perturbation theory of what you're doing there, you're cancelling out a whole load of error terms. And so I'm really regretting that I didn't put in the plot now, but you'll just have to take my word for it. You cancel out a whole load of error terms, and you can just see you get a much more accurate power spectrum that is basically as good as running a box of 8 times the volume, just from running 2 simulations of 1/8 of the volume, which have this particular relationship between them. So you can start pulling out all sorts of useful things just by doing this operation. Okay, so that's slightly off the track of what I wanted to say. I'm going to go back to the galaxies and just recap. So what we have is a technique where you can really run controlled simulation sets within lambda CDM. So you stay within lambda CDM cosmology, and you can make incremental changes and really see how your galaxy formation physics responds to that. And the kind of things we've been playing with, mainly merger histories and masses, but you can also play with angular momentum, with velocities, with substructure, and so on and so on. Right now, the only thing you'll find about this on the archive is a paper from Nina looking at dark matter concentration parameters, but do take a look. We've got an application to quenching, which I just showed you where we are with that. That's in preparation right now. Giving you a hint at some of the large-scale structure things we're doing. There are an awful lot of projects that we can think of to do with this initial conditions code, and we're essentially manpower limited at this stage. So if you're interested in joining us and having some fun with this, then please do just come and talk to me. Thanks for your attention. Wayne?
Really great. I like this.
Thanks.
The large-scale structure thing. So normally what you find if you look at the simulations is that the vast majority of particles go into halos, go into collapse objects. In fact, a naive Prashekta prediction is everything should be a collapse object, okay? But in ellipsoidal collapse it's not necessarily the case, but 60-70% of things should be in a collapse object. Now when you reverse it, the 30% that was not in collapse object, but you again expect 70% to be in collapse object. So is it true that you indeed found that about for 20-30% they flipped from being in a void to being in a halo?
Yeah, so I tell you one of the things you do find, which perhaps isn't totally obvious from this slide, is that a lot of the voids, so the voids spread out, but you find that there are a lot of halos right on the edge of voids, which tend to be from halo particles in the reverse simulation. So there are particles that are in halos in both, but they tend to sit on the edge of the voids, if you see what I mean.
If I have understood correctly, the GM technique is equivalent to go to a cosmological simulations, finding a halo whose initial conditions are a slight perturbation of those of another halo, and then zoom in on that one and compare with why do you gain? Where do you save time, or how do you increase accuracy? Isn't it equivalent of zooming in into slightly different halos?
Sure. The major difference is that it really is differing minimally, okay? So sure, you could go and take a huge volume and just pick out different regions which are almost the same, and so just sample it in that way, and yeah, absolutely, that's a perfectly valid thing to do. But you would need like an infinite volume before you found a region that was that similar to the one that we end up with. That's the difference.
Could you comment on this delta chi-square quantity? And for example, if delta chi-square equals 4, does it mean that this is a very low probability scenario? Or what does that mean exactly in terms of?
It doesn't mean very low. So e to the minus 4 over 2 is a tenth, right? So it basically means that if you look at the new structure you've created and compare it to the one you started with, it's 10 times rarer in the universe at large.
I don't think that's a fair statement.
Okay.
Because that assumes that, suppose you accidentally started by picking a very weird, specific area. You could actually make it more likely, right?
You could do, yeah, sure.
You notice that you
Yeah,
make it always less.
No, but delta chi-square can be negative.
Then negative.
And so if it can go negative, and then of course you create something more likely. Yeah.
All right, very interesting. Let's thank Andrew again.